Okay, one awesome application of considering the universal law of gravity is in orbits. Okay. Now, many of our planetary orbits and satellites, the moon, their orbits are nearly circular. Okay. And if they're circular, we have all of our power of circular motion to work with. So, for example, let's say, here's the Earth and here's the moon or a satellite moving around it in a circular orbit. That was a pathetic circle, but pretend it's a circle. And it does have a radius here, so this is r, which is some height bigger than the radius of this object. Let's just call it the Earth, just to be succinct. Okay. Now, at all times, the force of gravity acting on whatever object's out here is straight in. Okay, that's the force. It's a radial force. So, since the gravitational force is a radial force, or at least it's pointing, better yet call it a central force, but if it's circular motion, then it's a radial force. Then we have the relationship, say, and it's the only thing acting on it. There's no ropes or pulleys or pushes. We'll assume there's no thrusters on this object, whatever it is. And so we can say that the gravitational force, or Gmm over r squared, in magnitude, we've taken care of its direction already, is going to be equal to the radial acceleration, which we're assuming is pointing inward, times the mass. Okay? And we know that that radial acceleration is the tangential velocity squared divided by the radius. So because our gravitational force depends on distance, and our radial acceleration depends on distance, we have a simplification here. The masses already cancel out. And we can say that the velocity squared is Gm over r. Now, we've seen stuff like this before when you considered roller coasters and cars driving over hills and stuff like that, where the G, this Gm was slightly different, okay? But it had this velocity was dependent on gravity and a radius of curvature. Okay, so I'll just let you refer back to some of the previous videos to see that critical speed. But in this case, in all these cases, it was because gravity was the only force acting at that time. So what this tells us about orbits, about things orbiting a gravitating object, so like asteroids or the spaceships orbiting the Earth or something like that, there is a specific speed at every radius. So V and R are connected. You can't change R without changing V. If you do, it's still allowed. It's just it's no longer going to be a circular orbit, and this could jump out into an elliptical orbit, which that's a broader case of study, which we'll talk about in a second. Or it could jump into other types of trajectories that are just not circular. So if it's in a circular orbit, which is very important for satellites, communication satellites, and other types of satellites, they're all circular orbits. So this is a really important thing. So if I want to place a satellite somewhere out there at a certain distance, I have to get it going at a certain speed to match. I can't just adjust those willy-nilly. Okay, so this becomes a really powerful relationship. What's cool is it's related, having derived this from Newton's law of gravity, it can prove one of Kepler's laws, which was derived purely by geometry, purely by observation, looking at all the stars and how they moved, and saying, I measure all these things and come up with this relationship. Here we can prove it from a fundamental law of gravity and a fundamental relationship between mass, or between force and acceleration. Okay, so what I'm about to do, so this is a really important relationship. Next one is say, well, what is velocity? Okay, well, if you're in a circle, it's distance over time, and the distance is a circumference. So that's going to be 2 pi r squared, that's the circumference, over the time it takes, which we call the period, which is, so we're squaring both, since it's v squared. So we square distance and we square the time. So distance over time, quantity squared. All right, that equals Gm over r. Okay, now looking at this, I'm going to solve for this time. So take it up, take this r up, take this Gm down, and doing a little more careful, or a little more clearly with the t on this side, I'm I'm going to end up with a t equals a 4 pi squared, squaring the 2 and squaring the pi. And I have an r squared times an r. This r comes up, so I get an r cubed. Divided by, the gm comes down. Now, okay. This is one of Kepler's laws. It's saying the period of rotation squared is proportional to the cube of the radius. Really complicated. This is the most complicated power law we've looked at this semester. And so you might say, well, just take the square root of both sides, and you could. And you could say that the period is proportional to the radius to the 3/2 power. And that's something you could plot. You could do a log-log plot, and you can verify that. And that's basically what Kepler did, is he looked at all his data and saw that consistently the power, or the period was proportional to the 3/2 power of the radius of the orbits he observed. Okay? And then was able to come up with this constant that related the two. Okay? Oh, sorry, I take that back. Newton came up with the relation, the constants here. Kepler is only able to see a proportionality constant. Okay? But the actual what these constants were came from Newton's law. Okay, so the result we just found is also really powerful, a very good observational tool for looking at orbits in space. Okay, now another one that I want to look at, applying these ideas, is the relationship between this velocity and the potential energy of a circular orbit. This is really interesting. Okay, so I'm going to go this way now. V is the V squared is connected to kinetic energy, right? If I multiply this by 1/2 m, I get a 1/2 mv squared. I get a 1/2 mv squared. Well, that's going to equal this times 1/2 m, which is 1/2, and I'll put the m inside that. But what is this? That is the negative of the potential energy. So what we're saying is that K is equal to a negative 1/2 U for gravity for a circular orbit. Mind you, this is only for a circular orbit here. Okay, but K is equal to negative 1/2 potential energy because the velocity is correlated to the distance. It also means the kinetic energy is correlated with the potential energy. Now, if this isn't true, it means it is not in a circular orbit. It's deviated. Okay, but many orbits are, and then we can use these for man-made orbits like satellites, which are circular. Okay, so with this in mind, this gives us a kind of a powerful relationship that says, well, that means our mechanical energy, which is K plus U, is just simply equal to negative 1/2 U plus U, which is 1/2 U. Okay. All right. Now with that, we could apply this to a number of things. I'm going to do a next video about applying this to orbits and how you trying to get from one orbit to a different orbit, how these rules constrain that process.